Okay, so we're asked to find the, we're going to finish up section 3, which is polar coordinates. So we've got two examples. Find the volume of the solid z equals x squared plus y squared plus 3. So that's a paraboloid. And the so it's bounded on the bottom by the xy plane, which is the z equals 0. So when z equals 0, that means the xy plane. And then we have a circle of radius 1 in the xy plane. And above it we have this paraboloid, which starts at z equals 3 and then it goes up. So it opens up. So this, this solid that they're talking about, let's see if I can draw a picture of it. So here's x, here's y, here's z. So the paraboloid is going to kind of start at z equals 3 and it's going to go up, and then it's going to kind of go like this. And then if you draw this circle, you're going to circle in the xy plane. So this thing extends up as a kind of like a cylinder, but the top of the cylinder, instead of being a circle, is going to be kind of a indented arrangement. So if I can kind of draw this, so here would be the cylinder like this, but then the top is going to probably look something like, let's see if I can do this right. So instead of being a circle, it's going to actually be kind of collapsed, I would think. So it's going to be collapsed so that it has kind of an indent into it like that. So because the function that's describing the upper bound of the volume, which is this paraboloid, has x squared plus y squared, and the shape in the xy plane also has x squared y squared. This looks like a ripe, something ready for using the polar coordinate system. So what we have to do is we have to define the function z, which is the argument. So we replace x squared plus y squared with r squared, and then we have the plus 3, so it's r squared plus 3. And then we replace dy dx with r dr d theta. And as far as the region that we're integrating it over is this circle. So the polar coordinate representation of this is r equals 1. So if we draw the circle in the xy plane like this, you're going to have the radius is going to go from 0 to 1, and the angle is going to go from 0 to 2 pi. So the integral becomes this, which is z in polar coordinates, or in polar coordinates. This is dy dx. This is the inside integral, which involves the radius from 0 to 1, and then theta goes from 0 to 2 pi. So what we do is we integrate first. Well, before we integrate, we multiply r times the term, the height of the three-dimensional surface. So r squared becomes r cubed, 3 becomes 3r. We integrate with respect to r first. So the integral of r cubed is r to the 4th over 4. The integral of 3r squared, 3r is 3r squared over 2. We evaluate that between r equals 0 and r equals 1. Well, at r equals 0, it goes to 0. So you get 1 to the 4th, or 1/4. 1 to the 4th is 1. You get 1/4 plus 3 halves. 0, you get 0 for the lower limit of integration. So you add those together, you get 7/4. And then you integrate with respect to theta. So the integral of d theta is theta. You evaluate that at 2 pi and subtract the value away to get 0. So you just get 2 pi. So you get 14 pi over 4, which is 7 pi over 2. So that's the volume for that particular shape. And the last thing is find the area of this lobed structure, which has the equation r equals 1 plus the cosine of theta. So let's kind of look at what's going on there. What we could do is plot it as, we could have r and, well, actually we'll start off with theta. So let's say theta. We'll make a table up. So we have theta, which we'll specify will go 0. Let's say pi over 4, pi over 2, 3 pi over 4, pi, and see what we get. And so the radius is going to be 1 plus the cosine of theta. So here we get 1 plus the cosine of 0, which is 1. So you get a radius of 2. At pi over 4, you get 1 plus the cosine of pi over 4, which is the square root of 2 over 2. So you get 1 plus the square root of 2 over 2, which is 1.707. Square root of 2 over 2 is 0.707. Here you get 1 plus the cosine of pi over 2, which is 0, so you get 1. Here we get 1 plus the cosine of 3 pi over 4, which is going to be negative the square root of 2 over 2. So this is 1 minus that, so you'll get 0.293, I guess. So we take 1 minus 0.707. Get that. At pi, you get 1 minus 0. The cosine of pi is negative 1, so you get 0. So the way you would plot this is at theta equals 0, you have 2. At theta equals pi over 4, which would be here, this distance is 1.707. When theta equals pi over 2, you get a radius of 1, so that's that point. And then at 3 pi over 4, which is going to be this direction, you get this distance is 0.293. And when theta equals pi, which is there, you get 0. And then if you go through the same, so if you went to 5 pi over 4, that'd be the same as 3 pi over 4. Here you get 3 pi over 2, 7 pi over 4, 2 pi. So then you get this other part of the lobe. So to find the area, what we're doing is we're going to use the iterated integral, and we're going to integrate from 0 to 2 pi. So that's the outside integral. That's the d theta part. You've got then r dr d theta, well, r dr d theta. So that's the other part of the thing. And we are going to integrate from r equals, what are we going to do here? So the inside is r equals 0. So that's the, if we think about going from the origin out to here, because this is all filled in. If you think about a little incremental d theta thing, so the inside is just the origin, and the outside is going to be r1 plus cosine theta. That's the outside radius. So the And we don't have, this is like an iterated integral with area where you had here you had from x equals something to x equals something, which were the upper and lower limits of the area, and this was from y equals, actually this is y equals something to y equals something, this is x equals something to x equals something. And then we had dy dx, and we had nothing in here except dy dx, so it's the same kind of deal since we're calculating area and not volume. So what we do first is we integrate the first thing with respect to r, but we've got r dr, so when you integrate that you'll get r squared over 2. We evaluate that between 0 and 1 plus the cosine of theta, and then we have our d theta. So the integral of r dr is r squared over 2. And then we plug in the limits. So we get 1 plus cosine theta quantity squared over 2. And then you have minus 0 squared over 2. And then you put a d theta there. So we get 0 to 2. And if we square this, we'll get a fourth. In the denominator, well, no, I get a 2 because the 2's not in the parentheses, so it's just 1/2. And we get 1 plus 2 cosine theta plus cosine squared theta times d theta. And we've got to use the half angle the power reducing formula. So let me find that in the book. So under trig identities, we replace cosine squared theta with this. So we get 1/2 the integral from 0 to 2 of 1 plus 2 cosine theta plus, so cosine squared theta is 1 plus cosine 2 theta over 2. The whole thing times d theta. So we'll get 1/2 the integral from 0 to 2. And so we have 1 plus a half, so that's 3/2. So we get 3/2 plus 2 cosine theta plus cosine of 2 theta over 2, all times d theta. And now we integrate it. So we'll get 3/2 theta, because we're integrating with respect to theta. The integral of the cosine is the sine, so we get 2 sine theta. We integrate 2 cosine theta. Now we integrate cosine of 2 theta, we'll get plus, well, we have the 1/2 because there, and then because we're integrating, we're going to divide by a half because of this 2 theta. U would be 2 theta, so du would be 2 d theta, or d theta equals du over 2, so we get another half, and then we have the sine of 2 theta. So that's the integral. We integrate between 0 and 2 pi. Forgot 2. Where did I forget the pi part here? There we go. 2 pi. So we get 1/2 times 3/2 times 2 pi. I'm going to go ahead and do the 2 limits. 2 pi minus 0. Then we get 2 times the sine of 2 pi minus 2 times the sine of 0. And those are 0. Sine of 2 pi is 0. Sine of 0 is 0. And then you get the last one, we'll have 1/4 times the sine of, instead of 2 theta, 4 theta, because it's 4 pi instead of 2 pi. because you multiply it by 2. So you get sine of 4 pi minus 1/4 times the sine of 2 times 0, which is 0. So that's 0, and that's 0. So the only thing that's left are these two terms. This term at the beginning, and this 2 cancels out that 2. So we get 3 pi over 2. And I'm going to go check this answer because I've never worked this problem before. Well, I got it right. Sometimes I amaze myself. Okay, so yeah, that's the answer. So let's kind of review what we did. Is we used the double integral to find an area. And the big difference here is that we have this r d theta, and that's why we didn't talk about it, I don't think, in chapter 10, where we did talk about polar coordinates, but that was not for finding the areas, apparently. Okay, so here's your homework assignment. Just so you know, yeah, you have one of these area problems. First couple, you just deciding whether to use polar or rectangular coordinates. Typically, if you have some kind of circular symmetry, then you use polar coordinates. The next bunch are just describing regions using polar coordinates. And then you got to do some double integrals. Okay, so that's it for section 3. So we're moving on to section 4. I'll do my best here. So section 4 has to do with centers of mass and moments of inertia. Now we're going to come back to this topic when we get to triple integrals. So what we're talking about is a special case of if we have some kind of shape and we want to find the center of mass of that shape. So we can define our coordinate system anywhere. We don't have to define it. You know, what we're doing is there's, I guess, 3 things we're going to be doing. We're going to be figuring out what the mass of an object is, which doesn't, you know, where the mass is located in space doesn't affect what the mass is. The second thing we're going to do is we're going to find the center of mass. And the center of mass we kind of talked about in physics. If we had, when we were looking at beam problems, and if the beam was uniform, we said the center of mass was in the middle, and we could model or do the Newton's second law problems, assuming that the weight of the object was applied at the center of mass. As I said, we typically looked at situations where it was just a uniform beam, and therefore this geometric center was the center of mass. And what we're going to do is we're going to figure out what the center of the mass of an object is. We are limiting ourselves to what are called lamina. And basically what that means is that in the difference in density, which is the thing that's going to vary, is only in the direction in 2 directions, not in 3 directions. So what we would assume is we have something like that, a plate, and we're going to define our coordinate system, say x and y, within that plate. In the z direction, there's no change in density. So now when we get to triple integrals, we can deal with density changing in 3 dimensions. But so density is constant at a particular value, x and y. That's not true. So the density can change in the x and y direction, but for given x and y, the density is constant. Okay, so the density varies with respect to x and y. So in our case, we've been looking at these double integrals, the integral of f of x, y times dy dx or dx dy, and this has been in the past, has been the z coordinate. In our case, we're going to have a density as a function of x and y. So the function is density and not height. And we're going to look at that, like I said, over a particular shape that has a shape in 2 dimensions, but then in the 3rd dimension it's uniform, both in density and thickness and things like that. So we start off with mass, and in a general sense, if something's uniform, the mass is equal to the density of the object times the volume. So density typically has units of kilograms per meter cubed, and volume would have units of meters cubed. Now, because we're dealing with these lamina situations, the mass for lamina, so this is the case of uniform density, and it can be if we know the volume of an object, which if we were figuring out the volume of a 3-dimensional object, how would we figure out what that is? Well, we stick it in a liquid bath, immerse it, and see how much the height increases, and then that height could be multiplied by the cross-sectional area of this thing that we're storing it in, and you calculate the volume. If it was a complicated shape, if it was a sphere, we'd measure the radius or diameter of the sphere, and we'd use 4/3 pi r cubed to find the volume. So there are ways of finding the volume. Okay, now for lamina, we say the mass is the density times the area. But the density in this case is not kilograms per meter cubed, but it's kilograms per meter squared. And the area is the area, which is in units of meters squared. It's kind of like charge per unit area when we deal with electrical stuff. So typically you're given a shape, and you're given, so if the density varies with respect to x and y, the mass is the integral over the region, which is the area of the thing that we have, times the density. The integral of the density is a function of x and y times dA. So if this is a function of x and y, dA is dx dy or dy dx, depending upon how you want to, which is the easier integral. Now, if it's in polar coordinates, then this would have density have to be a function of r and theta, and you'd use r dr d theta. So there's an example in the book. I'm going to pick an example out of the back of the book here, the back of the section. So these are examples 11 through 22, and since I've never done these homework problems before, I can pick any one of them. So let's pick, this is problem number 13. So it says the shape is y equals the square root of x, y equals 0, and x equals 4. So these 4 things give us the shape in the xy plane. So let's draw what this looks like. So we got the square root of x, it's kind of like that. Y equals the square root of x. We've got x equals 4, which is a vertical line. And we've got y equals 0, which is the x-axis. So this is x equals 4. This is y equals 0. So that's the area that we're talking about. And the density as a function of x and y is some constant times xy. Now, we don't need to know what the constant is. this constant is just to change the area, or the x times y values, into a units of density. But where that point, where the center of mass is, or what the mass is, doesn't matter. Now they're also asking us to do the center of mass, which we haven't got to yet. So we'll come back, and once we introduce the center mass, we'll come back and finish it off. But right now we're just going to calculate the mass. So the mass is equal to the integral. It's a double integral. The region goes from, so this is x equals 0 to x equals 4. So that's these limits. We're basing this on a vertical rectangle. So the extent of this rectangle define the x limits. The top and the bottom define the y limits. So we go from y equals 0, which is this line, to y equals the square root of x. That's the upper line. If we were just finding the area, we'd put dy dx, but we're trying to figure out the mass. So we put in kxy d, and we're going to integrate with respect to y first, and then with respect to x. And that's because these limits are y equals something. So once you formulate it, it's just like we've done before. So you get the mass is equal to the integral of from 0 to 4, and the integral of this with respect to y is going to be kx y squared over 2 evaluated between y equals 0 and y equals the square root of x. So we treat k and x as a constant. The integral of y dy is y squared over 2. We evaluate that, and we have a little dx that's out front. So we get the mass is the integral from 0 to 4 of k x times the square root of x minus square root of x squared. So let's factor out the 2 here. So we get kx over 2. Those are all constants. We get the square root of x squared minus 0 squared times dx. So k over 2, the square root of x squared is x. So we get x times x minus 0 from 0 to 4 of k over 2x squared dx. Okay, so now I can integrate it. So the integral, I can bring the k and the 2 outside, and the integral of x squared dx is x cubed over 3. Evaluate that between x equals 0 and x equals 4. So we get m is equal to k over 6. So 2 times 3 is 6. We get 4 cubed minus 0 cubed. So 4 cubed is 64. 64k over 6, or 32k over 3. So let me just pause and make sure this is the right answer. Okay, success. So that's the mass. Now, the next topic is mass moment. Because what we're doing next is we want to find the center of mass. And if we go back to our simple case here, and let's say if you have, let's assume that this actually the beam has no mass, and we have a couple of masses that are sitting on this beam. And the center of mass is going to be where I put a fulcrum, and the sum of the moments equals 0, so that this thing is in equilibrium, that it doesn't go this way or that way. So the question is, what is what is x. So let's define x equals 0 here. And then this is actually x, the distance to here. So what is the distance there so that this thing balances? So the way you do that is you got, say, this distance here, which is, we'll call this x m1, and then the distance from here to here is x m2, and the distance from here to there is x m3. So those are the distances from this fulcrum point. So if we sum up the moments due to these you multiply by the acceleration due to gravity to do torques, but they're all multiplied by g, so the g's kind of cancel out. So what you'd have is, if I did some of the torques, sort of. Well, we'll do the torques. Okay. So equals 0. Because what we want to do, the whole idea of the center mass is to replace all three of these masses with one mass at a certain location. And that location would be, if I only have one mass, it has to be right at that point where you're going to balance things out. So this distance x sub m1 is really, we've got the distance, if we sum the torques around this point, the left side, you're going to have this distance, which is x sub m1 prime, we'll call it. And then you'd have the same thing here, x sub m2 prime. This one's just x. And this would be x sub m3 prime. And so you would figure out what the torques are. And so you do it, you could see that x sub m1 plus x sub m1 prime is going to be equal to x. So the distance from here to here plus the distance from there to there is this unknown distance x. So you could write the one that I'm going, well, yeah. So the one that I'm going to use for the torque is x sub m1 prime. That's the distance from here to here, but I can write that in terms of so x sub m1 prime is equal to x minus x sub m1. So I'd use this equation, this number, to calculate the torque due to this mass. And I could do the same thing for that, and I could write all this in terms of this unknown variable x, and then I could solve for it. And that would give me the center of mass. So that's the general concept here. So if you want to read the details in the book, you can. But what we do is we define these, what we call the moment of mass. So it's not like moment of inertia. It's moment of mass, which is similar calculation. If you remember, moment of inertia from physics was equal to mr squared. So there was this distance squared. When you do the moment of mass, it's not squared, it's just multiplied by the distance. So what we end up with is this quantity, which we call the mass moment of inertia, a mass moment with respect to the x-axis. And that's the double integral over the region of y, which is the distance from the x-axis. So these are with respect to the x-axis. Y times the density function of x and y, which we had previously and on that previous example, times dA, which is going to be dy dx. And the mass, moment of mass around the y-axis is equal to the integral over the region times x times rho of xy. this varying density times dA. So these give you the mass, moment of mass about the axes, and then the coordinates of the center of mass, which we're call x bar and y bar, is equal to the coordinates you take to find the x coordinate. You take the mass moment around the y-axis and divide by the mass, and then you take, to find the y coordinate, you take the mass moment around the x-axis and divide by the mass, and that gives you the answer. So we've calculated the mass. We did that in the previous step example. So what we need to do now is calculate these moment of mass around the axes. And just like in physics, the point of some of the torques around didn't make any difference as far as the answer is concerned. So where the object is relative to the x and y axis is irrelevant as far as calculating where the center of mass is. Now what we're going to do is it is going to affect the center of mass relative to wherever you define this. So if I took this thing and just moved it 4 units to the right, what would happen is the center of mass would get moved 4 units to the right. So it does affect it in some ways, but it doesn't, relative to the outline of the object, it actually doesn't make any difference. So I'm going to insert a page here. So now we're going to find the center of mass, which we think is probably about right here. It has to be somewhere interior to this solid surface. Now if it was constant density, we could do the same thing. The mass would just be the area times the density per area, but so I'm just looking geometrically what I think is the center of the area. That would actually be called the centroid. So the centroid is the point which is at the center of the geometric center, assuming constant density. But if you have varying density, then you have a little more complicated situation. Okay, so let's formulate what we have here. So the moment of mass around the x-axis is going to be the integral over the region, which is the same limits as we had before. So it goes from 0 to 4, and from 0 to the square root of x. Instead of putting the mass in here, or the density, well, we do put the density in, okay, but we multiply by y. So that's y. If we go back to the equation that we just wrote down, you have y times the density, but in our case the density is kxy, and then we multiply times dy dx. The mass moment around the y-axis is the integral from 0 to 4, and the integral from 0 to the square root of x times the density, which is kxy dy dx. So those are the mass, and then all we have to just take those and figure out what those are, and then divide by the mass, which we calculated was 32 pi over 3. So we're going to do each one of these. So m sub x is the integral from 0 to 4, integral from 0 to the square root of x. First thing I'm going to do is I'm going to just combine these two terms, multiply them out. So you get ky xy squared dy dx. Over here, we'll get k x squared y dy dx. So integrate with respect to y first. So the k and the x are constants. We get y cubed over 3 we're going to evaluate that between 0 and the square root of x, and we multiply by dx. Over here, we integrate with respect to y again, but y is just, it's not y squared, but y. So we get kx squared. That's a constant relative to the first integration. And so we get y squared over 2 evaluated between 0 and the square root of x times dx. Okay, now we evaluate the function at the two limits. Well, at y equals 0, we just get 0. So we're just going to evaluate it at the upper limit. So you get y, or x, this has to be a function of x. So you plug in the square root of x. So you get x to the 3/2 power. So the 3 comes over here, kx over 3. Square root of x cubed is x to the 3/2 power multiplied by dx. Over here, we've got the integral from 0 to 4. So we get kx squared. Here we have the square root of x squared, which is going to be x divided by 2. Plug in 0, you get 0 multiplied by dx. Next step is to simplify before we try to integrate. So you got x times x to the 3/2, so that's x to the 5/2. Divide by 3, do dx over here. Same kind of thing. M sub y is the integral from 0 to 4 of k over 2 x cubed dx. Now we integrate. So we have our constant k over 3. The integral of that is x to the 7/2 divided by 7/2. We're going to evaluate that between 0 and 4. Over here we have k over 2, x to the 4th over 4, between 0 and 4. So let's see what we get. We get 2k over 21. So we take the reciprocal of that. And then we put 4 to the 7/2 power. Over here, we'll get k over 8, 4 to the 4th power. So 4 to the 7/2, take the square root of 4, it's 2. 2 to the 7th is 128. Is that right? Get my calculator out. Okay, 4 to the 7/2, 128. So we get 128 times 2, which is 256 over 21. Is that right? Okay, yeah, 256 over 21. I think that's, I don't think you can simplify that any. 256 over 21, change to fraction. 250. Okay, so that's that. And the moment around the y-axis, that's 4 to the 4th, which is 16 squared, which is, I think, 256. 256 over 8. 256 over 8. Okay, but you can divide 256 by 8. That's 32, so you get 32k. Okay, so those are the mass moments. So to find the x coordinate, you just take 256 over 21k divided by the mass, which we calculated somewhere here earlier. Oh, it's 32 pi over 3, right? 32 pi over 3. There's no pi. 32 thirds k. Must be later here. Yeah, 32 thirds k. Okay. So that's so you got x is wait a second. Gotta go back one more page. Okay. So I'm going to cheat here. 256 divided by 21 divided by 32 divided by 3 and make that a fraction. You see the k's cancel out. So I get 8/7. I do the same thing over here. So my y coordinate, am I doing the right way or am I doing the wrong way? That's actually, this is y, because y is m sub x over m, and so the other one, x bar here, is this one. So you have 32k divided by 32k over 3, so that you get 3. So the coordinates are going to be 3,8/7. Okay, let's check this out. That's problem 13. 3 8/7. It's pretty good. Okay, so that's the gist of calculating the center mass. And so let's plot those points, 3 8/7. So 3 is here. The square root of 4 is 2, so that's 2. So it's 3 8/7. That'd be 1 halfway between. Well, yeah, here's 2. So that'd be 1 8/7 would be about right there. And that's because it's shifted a little bit compared to what I thought it might be based on just intuition, is because it's heavier, or it has higher density out here and out here, so it's going to be shifted towards that corner. Okay, well, I see it's 48 minutes. So what we'll do next time is we'll talk about moments of inertia. And the only difference with moments of inertia is you have, instead of y and x, you have y squared and x squared. Now we don't divide by the mass because we're actually, if the moment of inertia was mr squared, so we need a mass in there, so we don't have to divide by the mass, we just have to do the integral. Well, yeah, let's just write down what the results are. So the moment of inertia around the x-axis, or whatever axis you're doing, is going to be equal to y squared times the density as a function of x and y times dA, and the moment of inertia around the y-axis, which is the center of rotation. So you position your areas so that they're relative to the x and y axis, or where you're trying to figure out the moment of inertia around. So you get x squared times rho of xy times dA. So you can see with these particular cases that the only difference is that I'm going to be multiplying by one additional variable, but doesn't make the whole process that much different or more difficult. And again, these are for what are called lamina, which means that they're if you looked at them from top, they look like a two-dimensional object, but they have a thickness, and that thickness would have a constant density at a particular location the density would stay the same. Now, most practical situations are things are constant density. So these calculations here would be beyond most situations of what reality is. You don't make stuff. A lot of times you don't make things that have constant density. I mean, that are not constant density.